Okay, for our final example problem for the day, we have our relative velocity problem, where we have our police car, and not much of a police car. Ta-da! Now it's a police car. Chasing down a robber. Oh God, that's terrible. Unidentified green minivan. We are told a robber is going 120 miles per hour. So we have this, which is going to be our velocity of our robber, is 120 miles per hour. On the freeway, they are being chased by a police car going 150 miles per hour. So velocity of the police car is 150 miles per hour. If the police car is 5 miles behind them, that is visible, perfect. We want to know how long it will take the police car to catch up and how far the robber will have traveled. So with this, we're going to start again. We want to have what we know. We know that velocity of the robber is 120 miles per hour. Velocity of our police car is 150 miles per hour. And our we're going to call it a D. Our distance between the two is 5 miles. Perfect. That actually looks much better on the video than the screen. What we want to find. Well, we were asked for the time that it's going to take to catch up and the distance traveled by the robber over that time. Okay, well, we are asked for a time. Our equation for time, we have one equation so far that uses it, so we know it's going to show up somewhere, is x final is equal to x initial plus velocity times time. Except we don't quite have everything we need in order to plug into this. So x final and x initial, we can talk about this distance covered, but then if we're doing that, this velocity is neither my velocity of my police car or my velocity of the robber. My velocity is something in between. We want to convert these x's, we're going to go ahead and call them distances. So the distance between them final is equal to the distance between them initial plus what we call relative velocity. I can't just use VR because I use that for the robber, times the time. So if the velocity between them is x, that's the difference between their different velocities. This is how quickly this distance closes. So that is what we're trying to do. So we know that the first thing we need is this relative velocity. Okay, so we can say velocity relative is going to be equal to some function between the velocity of the police car and the velocity of the robber. And what we're going to do is we're going to think about how each of these impacts this distance, because we have an equation that I've already erased that is based off of distance. So the police car. The police car is going forward, it is chasing, and its goal is to close the distance. It is moving into this space between them, so it is going to be shrinking the distance. In order to shrink the distance, we need to have a velocity that is making it so we have a smaller distance, so that's going to be a negative velocity. The robber is moving away. It's trying to extend the distance, so it is making it so the police car has to go more than 5 miles to catch up to it. So it is going to be a positive in my relative velocity equation. So my velocity relative is going to be negative 150 miles per hour plus positive 120 miles per hour, which is going to end up with negative 30 miles per hour. And I'm just going to go ahead and add this. We have a velocity relative is equal to negative 30 miles per hour. We're starting to see the difference between the yellow and the green, just in that the green appears to be a dying marker. So the yellow is much brighter. Okay, back to my equation. I said that the final distance between them is going to be equal to the initial distance between them plus my relative velocity times the time that that relative velocity has to travel. My final distance, well, if the police car has caught the robber, there is going to be 0 miles between them. My initial distance, I know, I guess I can add an I to this guy, is going to be 5 miles. My velocity relative is going to be negative 30. I'm going to switch miles per hour to be written as miles over hours times my time. Okay? Move the 5 to the other side, divide by miles per hour. So I've got negative 5 divided by negative 30 is going to be positive 5 over 30, which is going to be 1 over 6. Miles cancel, so I end up with 1/6 of an hour is equal to my time. 1/6 of an hour, so we've got 1 over 6 hour is going, an hour is 60 minutes. So it's going to take about 10-minute car chase. So my time is 10 minutes or 1/6 of an hour. That one is complete. Okay. Then the other question that we have is my XR. How far is my robber going to make it in those 10 minutes? So that one, we just go back to our normal form. We have our final position is equal to our initial position plus velocity of the robber, because the robber is what's moving, times my time. X final minus X initial is going to be my delta X, that is the distance it has gone, is going to be the velocity of the robber, which is 120 miles per hour. And in order to make units work nicely, I can recall that my 10 minutes is just 1/6 of an hour. 120 divided by 6, delta X is going to be equal to 20 miles. So this is 20 miles. That's it. those are the problems from day one. Hopefully that helped